Thinking about quantum gravity. Today we start chapter 2. The whole truth is that quantum theory is approximate. Chapter 2a, we'll talk about a possible resolution of the quantum measurement problem, by which we mean we'll talk about collapse models. We do this in 3 parts in 3 videos. In this video, which is part 1 of 3 parts, we have a basic introduction to collapse models. In part 2 of chapter 2a, we have a more quantitative introduction to collapse models. And in the third part of 2a, we'll talk about current ongoing experimental tests of dynamical collapse. What does the quantum measurement problem have to do with quantum gravity? After all, we are discussing quantum gravity, not particularly discussing quantum measurement except in the context of quantum gravity. So why do we do that? The connection comes from the problem of time in quantum theory, which we discussed a while ago. I think this is the most central issue in quantum mechanics, how to get rid of classical space-time from quantum theory. It's absolutely essential. There's no way out. You have to have an underlying non-classical space-time. So once we have a non-classical space-time, we'll also need a mechanism to recover classical space-time. So we have to go away from the classical space-time because of reasons that we saw, the Einstein whole argument. We have to go away from the classical time, but having done that, we also have to recover classical time. And it turns out that a natural mechanism which allows us to do that, namely to go from non-classical space-time to classical space-time, a natural mechanism is spontaneous localization, the same mechanism which also solves the measurement problem. So that's how you see the connection. The underlying physics for using spontaneous collapse to solve measurement problem and to recover classical space-time from a non-classical space-time, underlying physics for both is essentially the same. It's spontaneous localization. And that's why we, while talking of quantum gravity, are talking of how the quantum measurement problem is getting solved. Okay, so this is a pictorial representation of what I just said. Level 1 is the deeper level. 2 and 3 we are familiar with. So 3 is classical mechanics on a classical space-time, 2 is quantum theory on a classical space-time, and 1 is the result of removing classical space-time from quantum theory. So we have a quantum theory, matter part is quantum, and the space-time part is also quantum. We'll call it operator space-time. We come back to it in future videos. Now these 2 arrows show that in order to recover the classical world, we easily can go to level 3. Level 2 is not the best level to go to from level 1. You can imagine that when matter becomes classical, space-time also becomes classical. Quantum matter and operator space-time go hand in hand very naturally. And on the other hand, classical matter and classical space-time go hand in hand very naturally. And the mechanism to go from level 1 to 3 is spontaneous localization. And then we use the same idea of spontaneous collapse to go from level 1 to level 2, and then from level 2 to level 3. Okay, so let's come back to the measurement problem. There have been various proposed solutions for this problem. We talked a little bit about this. These result from a reinterpretation or a mathematical reformulation of quantum theory. So these proposed solutions include the many worlds interpretation, Bohmian mechanics, consistent histories, and others. Since they all make the same experimental predictions as quantum theory, it really becomes a matter of personal choice as to which one is preferred over the other. So you could be a many worlds person, or you could be a Bohmian, you could believe in consistent histories, but they are all agreeing with quantum mechanics in their experimental predictions. On the other hand, consider the possibility that quantum theory actually breaks down in the domain of measurement and is not the right theory to describe the interaction of a quantum system with a measuring apparatus. Let's be a little bit more explicit about that. On the one hand, say you have an incoming quantum system which is microscopic, let's say, in terms of size or mass, in terms of atomic mass units, let's say 100, 1,000, 10,000, 10,000 atomic mass units. So it's made up of 10,000 nucleons, say. That is, let's say, the biggest quantum system that we have tested so far for validity of superposition principle. So quantum system comes to interact with a measuring apparatus which is macroscopic. So the apparatus could have something like 10 to the 18 atomic mass units, say. That's about a Planck mass. Or it could be bigger, more typically 10 to the 23 atomic mass units. So see the difference in the size of the micro and the macro system is huge, you see. 10 to the 4 AMU on one side and 10 to the 18 AMU on the other. There's a huge gap of 10 to the 14 AMU. We don't know. What is the physics there? Is it quantum mechanics? Is it classical mechanics? Is it a new mechanics like spontaneous localization? We don't know the answer. So you have a micro system suddenly coming and hitting a macro system. Maybe in this transition from the micro to the macro over 10 to the 4 over 14 orders of magnitude, maybe there is some new physics. We cannot rule it out. Okay, so that's what we mean by saying that quantum theory might break down. You have to allow for the possibility during a measurement process, quantum theory breaks down, maybe. Maybe there is a more universal dynamics, more universal than both quantum mechanics and than classical mechanics. Maybe there's a more universal general dynamics which includes a stochastic element responsible for the randomness. So we recall when the quantum system interacts with a measuring apparatus, superposition is lost. There's a breakdown of superposition and the outcomes are random. The breakdown is random. There's an element of randomness and probability in there. So why not consider including a stochastic element in the dynamics, in the fundamental dynamics? This is quite unlike the rest of physics, where we work with deterministic evolution equations, but here we see randomness in experiments. So why not allow for the possibility of the dynamics itself being random? Okay, and then the new dynamics, which has this stochastic element in it, it reduces to quantum mechanics for microscopic systems and to classical mechanics for macroscopic systems. That's what we mean by the universal dynamics. So those are collapse models. In the micro limit, the stochastic aspect is extremely negligible. Clearly, for microsystems, the Schrodinger equation works well. It works beautifully. It is deterministic. So the stochastic aspect is supposedly very small, insignificant for microsystems. On the other hand, for macrosystems, it is so significant. The stochastic aspect is so significant that the dynamics starts looking like classical dynamics. We'll see how that is done. Any attempt to generalize the Schrodinger equation must obey severe constraints if it has to solve the measurement problem without contradicting the outstanding experimental success of the Schrodinger equation. So you want to make a universal dynamics, it's not easy, it's extremely non-trivial. You have to agree with all the experimental successes of the Schrodinger equation, and yet you want to change the dynamics so that you somehow manage to solve the measurement problem dynamically. So what are the requirements of this new universal dynamics that one is looking for? It should be non-linear so that it causes breakdown of superposition during a measurement. That is quite obvious. The nonlinear aspect must be random in nature so that outcomes of measurement are random. And also we want it to be nonlinear because deterministic nonlinearities generally lead to superluminal signaling, faster than light signaling, which we would like to avoid. So can't have deterministic nonlinearities. We can have stochastic nonlinearities. Those do not allow faster than light signaling. The new dynamics has to be non-unitary. It has to have a non-unitary aspect in order that the system is driven to one outcome. It's not enough to be non-linear. You also have to be non-unitary. Non-linear would just oscillate you between, say, one stationary state and another, but that's not what we want. We want a complete breakdown of superposition, a collapse of the wave function. Now, in general, if you introduce non-unitarity in the dynamics, it violates norm preservation. But norm preservation is essential for the Born probability rule to come out. So, the non-unitary evolution must be norm preserving. And there are very special conditions that can be done. Okay, and finally, the universal dynamics must also possess an amplification mechanism so that the nonlinearity is negligible for small masses and becomes progressively more significant for larger masses, right? So small systems should have very less nonlinearity, very less stochasticity. Large systems should have a lot of nonlinearity, a lot of stochasticity. That is what is the amplification mechanism, which should naturally be there in the modified dynamics that we are looking for. So there are all these constraints: nonlinear, non-unitary but non-preserving, and should have an amplification mechanism. Remarkably enough, such a universal dynamics does exist and was proposed by Pearle, Ghirardi, Rimini, Weber, and Diosi in the 1980s. So this is a spontaneous collapse theory. This is what we, in its most refined form, which is the one which is in vogue today and is being tested by experiments. The collapse model, this universal dynamics with all these properties, is known as continuous spontaneous localization, and CSL in short. There are very many variants of CSL around. They go under this general name of collapse models. One specific model is the Ghirardi Rimini Weber theory of spontaneous collapse. Often we call it GRW. We also call it objective collapse theories or dynamical collapse theories. And we'll talk a little bit about that now. So these are these various names that one would hear, and they all essentially work under the same principle which we come to now. Okay, the principle essentially decouples measuring apparatus from collapse of the wave function. We are no longer ever going to talk of a classical measuring apparatus in spontaneous collapse theories. So collapse of the wave function is a property of nature, nothing to do in particular with measuring apparatus. So measuring apparatus and quantum system interaction is one very special case where natural collapse happens. So what is spontaneous collapse? It proposes that the wave function of every elementary particle undergoes a spontaneous collapse at some rate lambda and gets localized in physical space to a region of size RC. So by elementary particle, we will choose a benchmark. We'll assume the nucleon is the elementary particle we have in mind. It's a neutron or a proton, that is. We don't talk of electrons in this context. It will be understood that there are some other elementary particles whose collapse we can discuss once we know what we are saying for nucleon. So let's go over it once again. So suppose a nucleon is in a superposition of two states, like nucleon here and nucleon there, or any other superposition in position space. The wave function of such a state will undergo a spontaneous collapse of the wave function at a rate lambda. That means lambda spontaneous collapses per second. That's what we mean by the rate. How often is it undergoing a spontaneous wave function collapse? So what we are saying is, whatever happens, whatever we see happening in experiments, when a quantum system interacts with the measuring apparatus, that happens all the time in nature. Nothing to do with the measuring apparatus. It's just that the collapse rate would be extremely rare for nucleons, but very frequent for macroscopic systems. So that's the idea. So spontaneous collapse is happening in nature all the time. Between every two collapses, the wave function follows the usual Schrodinger equation. So remember, in the measuring apparatus issue, what we have a quantum system undergoing Schrodinger evolution, and when it interacts with the measuring apparatus, collapse of the wave function happens. So now we say no. Collapse can happen randomly anytime, and it localizes a particle to a size RC, some size RC in physical space. So a collapse happens, it gets localized to RC, then again it starts a Schrodinger evolution. Then another random collapse happens to some other point in space, again around the size RC, and again Schrodinger evolution takes place. So you have this collapse, expansion, collapse, Schrodinger expansion, collapse somewhere else, Schrodinger expansion. So these two processes are competing with each other. The unitary Schrodinger evolution, which causes an expansion of the wave function, competes with the non-unitary process of spontaneous collapse. That is the modification of the Schrodinger equation to the unitary part at this spontaneous collapse, this non-unitary part. And in this discretized picture, we'll come to the continuous picture in a while. In the discretized picture, there are collapses, expansion, and collapses happen at the rate of lambda collapses per second. Now, how much is lambda? These experiments have to tell. See, in quantum mechanics, lambda would be 0 because there's no spontaneous collapse. Lambda and RC are two new constants of nature, empirical constants. I mean, ultimately we expect that when we understand spontaneous collapse in a fundamental way, maybe lambda and RC will get related to the already known constants like Newton's gravitational constant, Planck length, Planck constant, speed of light, those. So lambda and RC are right now proposed as phenomenological or empirical constants, which in the CSL model are assumed to take these fiducial values. You assume these values. I'll tell you later why these numbers. So lambda, the collapse rate for a nucleon. So remember, always the benchmark is a nucleon. So how often does a superposition state of a nucleon in two position states say collapse? Very, very rarely. Once in 10 to the 17 seconds, which happens to be the age of the universe, or 10 to the minus 17 collapses per second, and RC is assumed to be about 10 to the minus 5 centimeters. So why these values? These are the most conservative values which help in solving the quantum measurement problem. So any smaller value for lambda would make collapse models uninteresting because those values will not solve the measurement problem. Any larger values are okay, they'll be very efficient, but larger the value of lambda, the more you are departing from quantum mechanics. So remember, lambda going to 0 is the Schrodinger equation, it's quantum mechanics. Lambda large, say lambda 10 to the minus 8 per second, so huge lambda, it's simply ruled out by data that we know. A very large lambda means a huge departure from the Schrodinger equation. That much easier actually to solve the measurement problem if you have large lambda, but clearly large lambda would violate Schrodinger equation in a huge way. So you want the collapse rate to be as low as possible. So a nucleon in a superposed state essentially never collapses. So that's why you see superposition working so beautifully for microscopic systems. The wave function of a composite object consisting of n nucleons collapses at the rate n times lambda, and this is the desired amplification mechanism. And incidentally, this is not an assumption. We'll prove in the next lecture that if the collapse rate is lambda for a nucleon, then naturally for a composite object, a larger macroscopic object consisting of n nucleons, the collapse rate is n lambda. Already you can see the outcome, the physical outcome. Take a measuring apparatus, think of it as having 10 to the power 23 nucleons. The collapse rate is hugely amplified, 10 to the 23 times lambda. So if lambda was, say, 10 to the minus 17 seconds per second for a nucleon, multiply that by 10 to the 23, you have a million collapses per second. That is a collapse every millionth of a second. So see what's happening. You try to make a macroscopic superposition, it will collapse extremely rapidly in just a millionth of a second, and that is why you don't see macroscopic superpositions, just that they are very, very short-lived. So you already see how the measurement problem is going to be solved. Microsystems, superposition extremely long-lived, as long as the age of the universe. Macro systems, superpositions are very, very short-lived, say a millionth of a second. And if you go in between over these 14 orders of magnitude from micro to macro, you can take in between values for this number n of nucleons in a composite object. And the rate will be somewhere between 10 to the minus 17 and 10 to the 6. Yeah, you get the point. The CSL effect is mathematically described by a stochastic non-linear modification of the Schrodinger equation, which satisfies the constraints we just mentioned above. So essentially, CSL converts the quantum linear superposition into an approximate principle. In the Schrodinger equation, superposition principle is exact. It holds forever until the system meets a measuring apparatus. Unlike in quantum mechanics, in these collapse theories, this modified quantum universal dynamics, the superposition principle is an approximate principle, meaning the superpositions are very, very long lasting for small systems, which is as good as lasting forever. And they are very short-lived, last for very small times for macroscopic systems. So superpositions hold, they do hold, but they don't hold forever. How long a superposition lasts depends on how big the system of interest is. If it's a macro system, very short-lived. If it's a micro system, very long-lived. And there is a trend in between. As we'll see in the next talk, CSL provides a solution of the measurement problem, and it explains the classical nature of macroscopic objects. However, this is a somewhat subtle point. The Born probability rule is not really proved in CSL. It's essentially built into the assumptions of CSL. Namely, we assume that even after adding non-unitarity and non-linearity and stochasticity, norm must be preserved. Why do we want norm to be preserved? Because we want the Born probability rule to come out. If norm is not preserved during this non-linear evolution, we won't get the Born rule. So in the Schrodinger equation, you can prove non-preservation, but it's not automatic in a non-linear theory. You will lose the conservation of norm in a non-linear theory unless you impose it by hand as a condition, but then it becomes a deep question. Why should norm be preserved in a nonlinear theory? I mean, we know we want the Born rule out, but we want to prove the Born rule. We don't want to take it as an experimental input. So we'll come back to this in the later lectures. But as far as CSL is concerned, the Born rule is really built in, it's not proved. Moreover, CSL and collapse models in general make predictions for experiments. These predictions differ slightly from those of quantum theory for experiments that have not yet been done. See, as of today, all experiments that are done agree with both collapse models as well as with quantum theory, so long as you choose the collapse rate to be sufficiently small. So one is trying to do further more refined experiments in which either collapse models will be violated or quantum theory will be violated. Such experiments are currently going on, and that's extremely interesting. We talk about that in part 3 of this chapter, that in the currently untested mesoscopic domain, the predictions differ from those of quantum theory in a sufficiently large way that you can hope to test them. See, for large systems, it's spontaneous collapse theories, the CSL goes to classical mechanics. For small systems, CSL goes to quantum mechanics. But in this meso domain, neither too large nor too small, which is an extremely hard domain to test experimentally, that's where we hope to find out whether nature obeys linear quantum mechanics or whether it obeys a non-linear theory like CSL. So in the second part of this chapter, it will be the next video. We introduce collapse models in a more quantitative way, and we prove how the measurement problem gets solved. We actually see that in the form of a proof. And in the third part, we'll talk about current ongoing experiments to test and confirm or rule out spontaneous localization. So that would be all for today. Thanks for listening, and I'll see you next time.